Yeah, so basically now we'll just basically read two files. First one is basically a case of simple linear regression. So we'll basically read a file, then basically run your gradient descent method to find the optimal set of weights. So yeah, you need to read it from the beginning. So you have read your data. So how do you read it? Is just use since it's a text file, you can directly use your Pandas CSV method to read the file. So in the first block where you basically read your file, in the second block is where you have actually loaded the data. So we'll have just a brief look at the data diagnostics. So we basically in this we are basically getting to know what's the population, what's the profit, and all of that. In this, we're basically getting to know what is the data type of each column, or what's the unique value, things like that. Okay. And in the next one, basically we'll look at plots. It was the main assumptions of linear regression. Right? One of the central assumption of linear regression is your both x and y, the relation between x and y should be linear. That's what we are looking at. So in this, you can clearly see there is a sort of a linear relationship over here, right? So your relation between your population and your profit, there is a sort of linear this thing over here. So this is what you're basically computing your cost. Costs again, it's nothing but your mean squared error. So I think the previous few sessions we had a sort of very detailed discussion on how to calculate mean squared error, how to calculate its partial derivatives, how to calculate its derivatives, and so on. Right. So that's what is happening over here. So we're just inserting a new value over there just for intercept. You can look at the data. So it's basically a tuple. Now we are basically selecting the column, selecting the x, selecting the y. So we'll basically calculate what is the mean squared error without sort of any optimization. Okay. So your mean squared error is 32. So this is with only your initial values. Okay. So you haven't sort of optimized your cost function so that you can get better values and things like that. So none of it has been done. So in the next step, basically what we'll run is we'll run a gradient descent. Again, so this is one more variation, one more easier way of writing gradient descent. In the previous example, I think we had multiple functions. So basically that was written mainly just to make sure you understand what has happened in gradient descent. So this is more sort of a cleaner way of writing gradient descent. So this we are running gradient descent now. So let's say we just run this file. So I'll explain in a bit what is alpha and itis. So in this you can see these are beta naught, beta 1. We are computing the cost. So as you can see, so after you run a gradient descent, there is actually such a huge drop in the mean squared error value. Right? So this is sort of the minima. Now, one more this thing which is different is what is the difference between this? So there's something that's called as parameters and hyperparameters. So basically, what is the difference between parameters and hyperparameters is parameters are which are basically which are picked up from which are learned from your data, I would say. So you have your weights, right? So weights are actually learned from your data, your beta naught, your beta 1. So those are the terms which are actually learned from your data, right? So you're not sort of assigning it. Obviously, you are assigning the initial values. But other than the initial value, the remaining values is sort of the model is sort of picking from the data. It's sort of not picking, sort of learning from the data, right? So running from the data to gradient descent or any other method or any other optimization algorithm is sort of learning from your data, right? That's what our parameters. What our hyperparameters are? You're supposed these are sort of values which the model is not learning from your data. So these are the values which you can basically you need to input, the user need to input. Obviously, there are default values as well, but the user, I think user is supposed to input values for better results. At least in certain cases, you can't be sure that whatever random value you enter will definitely get you better values. But suppose if you know how each of these hyperparameter behaves, you basically work around with that. So this is output where we have a line, okay, where we basically have a line where we're basically just trying to predict the profit as well as the population size. So this is a fitted line. Okay. So in the next example, basically we'll look at what basically happens. as the number of iterations increases. So how is the how is error varying with respect to the training epoch? So one thing you can see, as the number of iterations increases, right, your cost value drastically decreases. So at least in the first iteration, you see a huge drop in the cost. And I think for this particular data set, since the data set is fairly small, you don't see much of changes after a number of iterations. But usually, if you have a data set in few millions, right, so only after few hundred iterations only will you see a loss value getting stabilized. But for now, there is no stabilization, or there is no this thing in loss value. So this is an example of mainly a simple linear regression. We're just having only one independent variable. We'll also look at a case where we have more than one independent variable, right? So we basically have multiple independent variables. So this is basically a data set where what is the problem statement is, you're basically supposed to predict price of a house, given the size of area of the house, and the number of bedrooms in the house. So these are few pre-processing steps which we are just running. Right. So now in this, basically what we're doing, we are adding additional ones column. So all of these steps are more or less the same as what we had done in the initial simple linear regression. That's why it's all been put it in a single listing. So this is the value, this is the cost with the current these things. So this is the value of the cost after you run the gradient descent. We can actually check these values without running gradient descent, but it should be on a higher range. So maybe when you run this graph, you'll basically understand how does the cost vary. So as you can see here, the cost varies maybe after, so there's no sudden drastic drop as in the previous case. So in this particular case, you see a sudden drastic drop. But in this particular case, in this particular multiple linear regression case, you don't see a sudden drastic drop. So there is a drop only after maybe around 150 or 200 iterations. Is only after that you basically see a drop in the iterations. Yeah, so this is what when you run a multiple linear regression example. So next we'll basically try to fit the same data using Scikit-Learn. Okay. So what basically Scikit-Learn generally is the preferred machine learning library. So in general, if you want to run any machine learning model in Python, at least, it's always preferred if you start looking at it in Scikit-Learn. So I think we'll have one more session where we basically try to understand how Scikit-Learn is built and how do you call different algorithms and all of that. But for now, we just fit a simple linear model. You just do a simple linear model dot fit. Right? We just fit the third line. The first line is where we are basically initializing the linear model objects. In the second line is where you're first line is where you're importing the object. Second line is where you're sort of initializing the model object. Third line is where basically the model is being trained. The model is being trained or model is being fit. That is what's happening in the third line. Okay, so you're just you're just importing, creating the linear model, then you're fitting. So you can just have a look at it. So we'll have a detailed. So there is a detailed session on Scikit-Learn. Maybe you can just check that, just to have understanding of how to actually use Scikit-Learn and how Scikit-Learn actually built and all of that. Right. And the type of model is a linear regression. Then yeah, this is sort of the output from your sklearn model. Okay, this is what basically is output from your sklearn model. So this is what is a simple linear regression, multiple linear regression. So we actually put it in code. So the one thing which is left is model interpretation. Okay, so model interpretation, as I think we had discussed in the previous session, model interpretation is what is one of the strong points of linear regression, and is what distinguishes it from maybe other complex algorithms. Okay, so how do you actually sort of interpret your results? Say just take an example of, say, you're trying to predict the number of bikes rented per day. Say suppose your problem statement is basically to predict the number of bikes rented per day, and your variables are, say, temperature, Then you have variables such as season. So the first one is a variable name. The second value is basically your weights. What is the weight of each one of this? Say you have a season column, you have a weather column, right? So then you have your humidity column. So what is the target? Target is basically predict the number of bikes, correct? What are the independent variables? One, you have temperature, other you have season, the next you have weather, humidity, and the next to it are the values of weights. So how do you interpret it as? So interpretation is actually fairly straightforward. How do you interpret the coefficients? Right? So how do you interpret the coefficient is, say, holding all of the features fixed. So keeping all features fixed. Okay. A unit increase in temperature. So keeping all other features fixed, keeping all other features fixed. Okay, keeping all other features fixed. Unit increase results in rental increase of 7.8 bikes. Okay. So you get the idea, right? So basically, when you keep all of the features fixed, so basically you don't change any of all of the features. So if the temperature increases by a unit value, if the temperature increases by a unit value, then the number of bikes which are rented increases by a magnitude of 7.8. Similarly, for season, weather, humidity, how do you interpret it? Since it's negative, right? So unit increase in humidity. So if there's a unit increase in humidity, there is a 1.11 decrease in the number of bikes rented. So it's not an absolute value; it's just a decrease, right? So you're not telling one unit increase in temperature results in 7 units. So it's not absolute value; it's sort of a relative value. We're just trying to understand. So yeah, this is okay. So this is what is linear regression, and we'll again meet in the next session. We'll basically continue with the next algorithms. Thank you.